So thanks so much for sticking around this long and coming to our talk. My name is Ben. I'm a recent PhD graduate of the university in Erlangen, now a postdoc in Saarland University in Saarbrücken, and I have the great pleasure to give this talk today with my colleague Sebastian, who's a PhD student at the Ruhr University in Bochum, and the third person in our team was actually Martin, who was not able to make it here, but he was still part of this project. So what's the project that we want to talk to you about, or let me give you a brief agenda of what's to come. So first, we're going to talk a little bit about the same origin policy, which most of you people might probably know, but still it's important technical background. Then we will talk about the concept of what we call cross-site script inclusions. And then we will generalize this kind of attack, and then Sebastian will talk about an empirical study we conducted on the web, and then finish the talk with the conclusion. Right, so the same origin policy is the most basic security policy on the web. So let's assume, for the sake of the argument, that we have an attacker that has successfully lured you as its victim to his site attacker.org. And on this page, well, he can obviously, because it's under his control, he can host arbitrary HTML, but also he can host some JavaScript. And now this JavaScript tries to gain access to a remote domain, in this case gmail.com. And one very important thing to note in this case is that since it's running in your browser, if you have cookies that are valid for gmail.com, then your browser will attach these cookies to the outgoing request to gmail.com. The reply will come in, and this would obviously be a really big security problem, right? Because in these cases, an attacker could, well, simply read all your emails from Gmail. And this is exactly where the same origin policy kicks in and stops the interaction, because it states that only resources which share an origin, and an origin is hereby defined as the protocol, the host name or IP address, and the port may interact with one another. And if this is not the case, then the same origin policy actually drops this connection or drops this access, thereby keeping your Gmail emails safe. However, it's slightly different for JavaScript. So if you think about JavaScript, you often think about jQuery, right? A lot of pages have jQuery, but a lot of them also don't actually host it themselves, but rather have Google, for example, host it. So there needs to be a way for your browser to include script content from a different domain. It's also often the case with advertisement, because if you have advertisement that's running on your site, you don't want to host the JavaScript yourself, but rather have the ad provider. And therefore, the same origin policy is somewhat relaxed for script inclusions. So it's perfectly okay to use script source remote domain, and your browser will actually fetch those scripts and then execute them in your page. And one very important fact in this case is that the included code inherits the origin of the including site. That means, let's say I have attacker.org and I include something from, say, I don't know, jQuery.com, then the code is actually running in attacker.org. That means they both run on the same global scope. And while this has security implications, if there are vulnerabilities in the third-party code, as we will see in this talk, it has also some security implications the other way around. So let's go back a little bit to 2006. Back then, Gmail was hosting a file called context.json, which would actually have the contacts of the user that was currently logged in. In this case, we see this user has John Doe and Jane Doe as his contacts. And what an attacker could do is he could, again, have his own website and then do the following. So he would do a script source of gmail.com/contact.json. But this doesn't look like valid JavaScript code, right? So it's not, it is valid JavaScript code, but it's not executing anything. However, there was a kind of a bug back then, which would actually allow you to override the array constructor. That means, in this case, the file would be included, and then the JavaScript parser would say, oh, this is a new array, so now I have to kind of invoke the array constructor, and thereby in here you could easily kind of steal this secret data. There were a number of similar attacks, for example with CSV files, where basically the JavaScript engine would interpret things as it shouldn't interpret them, because it looked like valid JavaScript, or even in one case I think was with Firefox, who wouldn't execute it, but it would give you an error message that would say some variable was not defined, and thereby you could leak the content of these files. However, cross-site script inclusion is basically an attack that is a little bit more widespread or widely defined. So the previous attacks, as I said before, with this array constructor, those are browser quirks. So these are issues related to the implementation of the browser. These have all been fixed, so doing that now will not work anymore. However, what we wanted to kind of see is, are there other ways to leak like private data? And one thing that all these attacks had in common is that they all used script source and then included some content that looked like JavaScript. But no one so far actually looked at what happens if I try to look at JavaScript that is actually being included in regular pages and just include that. Is there maybe some dynamic nature to those files? So are they only static, or is there some dynamic generation process involved on the server side? And well, if that is the case, there is actually some dynamic component in there. Is there any sensitive user data in these scripts that might be dynamically generated on the server side? And then last but not least, whether it's actually possible for an attacker to leak this kind of information. And now I want to hand over the word to my colleague Sebastian, who will tell you a little bit about the methodology and then the discovered vulnerabilities.
Okay, thank you, Ben. So as Ben just told you, we are looking for JavaScript files, and we are specifically interested in JavaScript files that are generated by the server. And we are also interested in the user data, and user data is usually like somehow connected to a user session. So basically we are looking for JavaScript files that are generated based on the user's authenticated session, and that is mainly the cookie. And for this purpose we built a system that would detect such scripts and just report them to us. And with this system we then conducted an empirical study to see whether we find sensitive user data in JavaScript files and whether we can leak them across domain boundaries, similar to the attack that Ben just showed. So let's have a look at the detection system first. So basically what we build is a browser extension. So here we, with a normal browser, we just visit a website, which we here call vuln.com, and this vuln.com might have a legitimate script that this site uses to provide some functionality. And what we would like to find out is if this script is dynamically generated and has the user data inside. So we built a browser extension that runs in the browser, and while we browse vuln.com, it would fetch all the scripts from the page, and it would try to find out whether there is some state-dependent generation going on. So what the extension did is it requested the script twice. So it once did it with cookies, so with in the authentication context of the user, and once without cookies. So we get two different, so if the JavaScript is static, we get basically the same file back. If it is somehow dynamically generated based on the user's authentication state, we should see some difference in the script. And that's exactly what we try to find out by diffing the two different responses. So whenever we see in the diff that there is like a change, we know, oh, this JavaScript might somehow depend on the user's state. So what we did then is we went to the Alexa top 500 websites and we registered accounts for the first 150 sites that allowed us to register accounts. So they had to have a registration form. It had to be possible to register free of charge without paying money, and also the registration had to be possible for us. So some sites required social security numbers of countries that we weren't able to get. And so we just registered to those sites that didn't have that. And then we went to those sites and manually seeded the sites with user data. So we were interested in whether scripts might contain user data, so we need to put the user data into the application first. So we went to all these sites, and for example, in a shopping application, we put things into a shopping cart, we created wish lists. In a social media or social networking site, we created an account and sent messages, or had entries to a wall or something. So that we get some private data into it. And afterwards, we used our extension to browse the site again and to use all the different kinds of functionalities and to go all the pages and like interact with the site and encounter all the different scripts that the site would use. And then our extension reported all the scripts that were dynamically generated. And these are the results that we found. So we investigated 150 pages, and we found out that 49 of the pages had some kind of dynamic generation of scripts, so dependent on the user session state. And we manually looked at these 49 files, and we found out that 34 of those files contained unique identifiers of the users. So there was an email address or an account ID or a full name and a birth date, something that uniquely identifies you as a user. We then found that 15 of these pages had scripts that contained other personal information, like your street address, I don't know, your maybe your shopping cart entry, your emails, or your banking information. And we even found 7 pages that had CSRF token or authentication tokens in scripts. And so it seems that there are a lot of JavaScripts that are dynamically generated, and yes, JavaScript files contain very sensitive data. So the question is now, can we leak the data somehow, like the attacks that appeared in 2006? And for this, I quickly want to reiterate on the attacker model. So what we now have is we have a set of vulnerable websites. We have a website that we control. Here it's attacker.org, and we assume that we are somehow able to drive users to that website. So by sending out links via email or contact you in a chat or something. And in this website, we can include this script that is dynamically generated from vuln.com. And this would generate a request with the cookies of the users. And based on this cookie, the vuln.com would generate some kind of server-side, or would run some kind of server-side script and generate the JavaScript code. Then it would send that generated code back to the browser. The browser will just see, okay, this is a JavaScript file, so I execute it. And basically what we are trying to do is we try to poison this environment. So as we learned, this script, here this runs in the origin of attacker.org. So basically it uses the global scope of attacker.org. And we are trying to come up with some JavaScript that would poison the global the global space and the global functions that are available in that website, so to make this script leak the data to that functions. And basically I will only present the easiest and most obvious ones because of timing reasons. We found, I think, 5 different methods to leak global and local variables and so on, but I don't have time for all of them. So the first method is very obvious. So these scripts might just have global variables. So here are 3 different kinds of global variable declarations in JavaScript, and it might be just generate a variable that is called first name and contains the user's first name or the user's email address. And to leak this data is very easy. So the attacker includes this script in attacker.org, and then after executing the script, the global variable will be available in the global space, so the attacker can just access it. So by just visiting attacker.org, the attacker can learn who you actually are by looking at the scripts of the pages that you are actually logged into. The second approach is also very, very obvious. So what we saw is that websites usually split up their functionality. So they have like a base library that contains all the common functionality, and then they have like some business logic that would use the common functions and so on. And usually the base library is included as one script, and the business functionality is included as a second script. So what you can do as an attacker, instead of like including the common base library, you just write your own base library with the same set of function names, so that all the functions are available to the script. And then you just include this script, which will pass some sensitive user data into this library function here, and if you set it up correctly, you will be able to receive the data in the attacker. And here we can see it. So the attacker would just, in his JavaScript, declare his own library. He would set up the function that has the same name as this script, and then he can just access whatever data is in there. So these are the most obvious ones. We have also some methods where we can leak local variables that are not passed to global functions, but that's too complicated for just this 25 minutes talk. So we then tested all these methodologies against the scripts that we actually found, and these are the results. So of the 49 scripts or 49 domains that we found, we were able to exploit 40 of the domains. And the reason for not being able to exploit the other 9 is that for these 9 we were not able to guess the URL of the script. So the script that was dynamically generated had some kind of token in there. For example, a few websites use session IDs passed in the URLs, and we were not able to guess these tokens, so we were not able to like include the scripts within our page. But I think this was mere coincidence that we were not able to do. I think web developers are not aware at all of this issue, and nobody protects against it. I think it was just coincidence. And basically what we were able to achieve is from the 34 domains that had unique identifiers, we were able to leak these identifiers of 28 pages. So basically, this enables us to do de-anonymization. By getting a visitor to our page, we were able to tell his email address or his name, and so on and so forth. From the 15 occasions where we had personalized data in the scripts, we were able to exploit 11, and we found all kinds of things. We found phone numbers, we found email addresses, we found banking data, credit card numbers, and so on and so forth. And from the 7 scripts that contained CSRF or auth tokens, we were able to exploit 4 of them, and I will present a few of them soon. So now I would like to go over a little demo that we prepared, and I hope it works. We actually do this over the phone, because the phone is faster and than the network here and more stable. So you cannot see it, but that's actually a browser window. It's a website that we set up, so a website that we control. And I'm not going to show the source code of this website because these are actual vulnerabilities. So we contacted all of those 40 websites and told them, hey, you have a problem there. We got 3 responses of 3 websites, and 2 of them fixed it, and 1 of them didn't. So the first level support didn't understand what we wanted from them, and he just dropped the case. So we have plenty of examples to show. So let me quickly, these are buttons, we have 3 different things, and these will actually be pulled from different sites. So this could just be an arbitrary website that you visit. So the first one is quite interesting. So now it gets the script. I hope it works. Yes, it works. So it included the script from another page that I'm not going to disclose. It found in the script the name. This is our testing account. It found the email of this user, and it actually found the phone number of this user. And this phone number is actually Ben's, because on this side you had to provide a valid phone number. Then the next example is from a shopping site. So the shopping site allowed you to create wish lists on the shopping site. And this wish list was shown like in a widget on the page, and they used the dynamically generated script to get their data to the page. So let's request it and wait for some time. It takes a while because it's really slow. Yes, here it is. So here is the wish list of the big, quite popular shopping site, and you can see what the user and that's pretty interesting. You could like create a referral page where you offer these items to the person just visiting your website, because he's likely to buy the things, right? And then the other one is pretty interesting. So this is from an email provider, and the email provider has a small widgets on his web page and shows the 5 latest emails in that widget. And these emails were actually contained in a dynamic script, so we can just click and wait. Yes, there it is. We can scroll. Invert it. No, it doesn't really work, but you can see the first emails. So you can see, well, there was an email from this person, and you can see the subject, you can see the date of the email, and you get also a few technical information about the email. You're not actually able to see the content, but I think the subject is already like a nice thing. And you can also see how many unread emails he has in his account. So that's also an interesting fact. Okay, I need to go back to the slides now. Where's my mouse? Okay, we had a few more interesting examples, but some that are too complex to demonstrate. So I will go over two other examples. And this was a very interesting one. So we found a news website, and this news website had CSRF protection. There was not really anything of interest in the news site, but you could leak the CSRF token of the news site. So we used this XSSI attack to steal the CSRF token. And this now allowed us to do a CSRF attack. And well, we were not sure. It's a news site. It didn't have anything interesting. But we figured out that in the profile page of this news site, there is a cross-site scripting. But the cross-site scripting is only exploitable by the user himself, by changing his profile and putting a cross-site scripting payload. And it's also only a page that only the user himself can see. But well, we have a CSRF token, so we can just send a profile change request. So we did that, and I need to hurry a bit because of timing. And we executed the cross-site scripting payload, and from the cross-site scripting payload we were able to read the Facebook OAuth token that they had, because they had like this Facebook integration where we were able to log in, so we were able to access the user's Facebook account, and we were able to post in his name, for example. And this can enable you, for example, to create a worm. And I will quickly go over the other service. So this was the most severe thing that we found. We found a file hoster, and the file hoster had like a very AJAX-driven web UI where you could all kinds of fancy UI interactions. And to bootstrap this UI, this hosting provider used a dynamic JavaScript to pass the auth token from the backend to the front end. So you were able to leak the auth token, and with the auth token you were able to talk to the API. So you were able to do everything. You were able to read files, to write files, to delete files. And as an interesting fact, this file hosting provider had multiple other services. So they had email, they had calendars, and so on. And on each of these services, they had like one API where you could pass an auth token of another service and get authenticated to that service as well. So we were able to steal the auth token and then take over all the services that this company provided to users. Okay, I will quickly go over how to prevent these vulnerabilities in the first place. So, as opposed to the attacks that have been shown in 2006 and other years, our attacks are not based on browser quirks. So you cannot easily remove an array constructor call or something, but it's based on standard JavaScript features. And that's why we cannot fix this on the browser level. And basically, because of the other attacks that we also found that I didn't present, it's very hard to craft a dynamic script that is not leaking any data. So what we do as a recommendation is that you should prevent script files from being included by third parties. And you can either do this by strict referrer checking, which is very error prone, or by using secret tokens in the URL, so that an attacker cannot include your script in the page. But this is like only like a step that you should only do when you really need to have these dynamic scripts for whatever reason. What you really should do is you should separate your JavaScript code from your sensitive user data. So you should have static JavaScript and have a data provisioning service that is not like handed to the browser as a script file, and that will be protected by the same origin policy. And last but not least, I want to talk about one other topic which is quite of interest for web security people, and it's about the content security policy. So the content security policies is a new mechanism for basically preventing XSS by whitelisting JavaScript. And like from a high-level point of view, it requires you to externalize all your inline scripts to external files to later on whitelist the host. And what we saw in our investigation in the peer study is that a lot of these inline scripts are dynamically generated and contain sensitive user information. And usually inline scripts are not prone to our attack because you cannot easily include an inline script into an attacker page. But if you introduce content security policy and you blindly move out all your inline scripts to external files, then you will get prone to this attack. And I think content security policy in this case will make this issue a little bit more widespread. Okay, let's come to the conclusion. So we investigated the security of dynamically generated JavaScript files. We found that about 1/3 of the most 150 popular websites use dynamically generated JavaScript, and most of these dynamically generated files contain sensitive user data. And we showed some ways to leak this data, and we found out that we were able to leak data in about 80% of all the cases. So for the 49 domains, we were able to exploit 40 of them. And the consequences can range from simple privacy issues, where you get de-anonymized by visiting a website, or up to full account hijacking, where your whole account gets taken over by an attacker. And introduction of CSP might make this problem worse. With that, I would like to thank you for your attention, and feel free to ask any questions. Questions? There's a question.
So most of the companies use
Yes. Nothing, basically. We tried to contact them several times and they didn't react, so there's nothing really we can do. I mean, we could send them to full disclosure or something like that, but we didn't want to do that. Yeah.
What I did when comments didn't react, I sent it to someone where there are services available from staff and so on, and then they contact them and say, okay, 2 months you publish it, and then all of a sudden 2 months later, sing it.
Yeah, that's probably a possibility to pass it to some cert, yes. But we haven't done it yet. There's another question.
Did you look at popular content management systems or other web applications like MediaMeter or whatever? And another question is, did you release plugins?
So the first question, did we look at popular content management systems or other software? The answer is no. We just stick to the 150 pages. Because it was a huge effort to do that, just because seeding, we had to seed all these pages, right? We had to put all the different user data that you can imagine to be in such an application. We had then to find all the scripts. We had to manually click all the functionalities and so on. So we decided to limit the empirical study to these websites because we spent weeks in clicking websites and creating accounts and so on.
I think for MediaWiki, I mean, Wikipedia is kind of high up in the Alexa rankings, and we use that to really interact with basically MediaWiki, which is running on Wikipedia. So we didn't find anything there from what I recall. At least nothing we could actually exploit. That was interesting.
And the second question, do we have any plans to open source the tool? I think currently we don't have any plans. But the tool is really simple. So I think it's really like 100 lines of code. So you can create it from scratch really easily in like half an hour of coding. Yes?
So does the browser determine if it's JavaScript based on the content type sent by the server, or what does it determine?
We had a Chrome extension. And if you hook to the debugger API in Chrome, it will tell you where the request was coming from. So we looked at this type, and there's a type script, which if it came from a script, it has script in there. That's what we looked at.
I mean, you might have, in theory, you might have like XHRs, which are used to retrieve this, but then again, with XHRs, you can actually cross domain boundaries, right? At least not. But I think, yeah, as Sebastian said, I think there was another way we also looked at it using the mutation, mutation observer API. So basically, you would inject code into the page itself, and every time a script element was added, then we looked at the source for that.
So you guys basically did it based on cookies. So you basically sent a request with it or without cookies. Did you do anything else, like changing get posts or potentially other HTTP requests?
No, the only thing that we did to the request was removing the cookies.
I mean, I think I found one API which had some interesting get parameters in there. So I played around with it a little bit, but not in any depth or with any methodology behind it.
Any other questions? Otherwise, thanks again.
And, yeah, have a great night.